So without further ado, Dave Farley, can you take us away? Please, a round of applause to kind of introduce him.
Welcome. I'm sorry I was a little bit late arriving. I want to talk today about software and in particular engineering for software. I think that engineering is one of the more creative things that we as human beings do. And if you're not quite with me on that, suspend your judgment for a few minutes and let's try and see if I can convince you otherwise. So I think often we kind of think about software projects in sort of strange ways. And one of the things that seems normal for me is that there's no normal distribution of software project success. If software projects were normal things, there'd be as many software projects finishing ahead of budget, ahead of schedule, under budget, and delighting their users as were finishing over budget, late, and annoying their users. But I don't think that's what we think of as normal. I think normal is more skewed like this for us. And I think that's saying a few things, but one of them is quite profound. I think what that's saying is that we've got the model wrong. We've got the way in which we think about and approach software development fundamentally wrong. And I think what that means is that we require some kind of paradigm shift. This is my lovely little diagram of a paradigm shift. On the right-hand side here, these pictures are meant to describe the orbits of the planets based on two different models of the way that the orbits of the planets works. On the right-hand side of the screen is the geocentric model of the solar system. This is the model that was held for probably tens of thousands of years, certainly thousands of years, and was held until relatively recently, until only a few hundred years ago. And the assumption here was that the Earth was at the center of the universe and that everything revolved around us. And that's fine as far as the orbit of the sun goes and the stars and the moon. And then there are these annoying things called planets, which just seem to wander all over the sky when you try and figure out where they're going to be next. And that confused people, and they built complicated machinery in order to be able to predict where the planets might be, the most complicated machinery that people had built up to that point in history, and so on. What it took to correct this problem was a change in perspective. And in this case, the change in perspective was to say, no, it's not the Earth that's at the center of everything. It's the sun that's at the center of everything. That's still not quite right. We're actually not at the center of everything. We're zooming around a galaxy. But it's much, much more accurate in terms of the orbits of the planets. And so we end up with a much simpler model. And so the perspective that you take in trying to figure out where you view things from is important. And I think that's one of the ways in which engineering as an idea matters for us. So what does software engineering really mean? I think what we often think it means is stuff like this. And I think this is a big mistake, but it's a big mistake that we've been making in software development, nearly all organizations that practice software development, for at least the last 50 years on and off. And so this is confusing manufacturing with engineering. None of these pictures are pictures of engineering. Engineering happened before these pictures were taken, but the pictures that we're seeing here are of manufacturing. That's a cookie cutter process that was generated for predictable problems. But this is not our problem. This is never our problem in software. Our problem in software is very, very different. In software, we do stuff like this. We start out with some code of some kind. Through a variety of different approaches, we generate from that code a stream of bytes. And now one of the unique things about a stream of bytes is that however big that stream of bytes, we can reproduce it perfectly for essentially zero cost. So we don't have a production problem. We never have a manufacturing problem. Our problem is entirely different. Our problem is the problem of designing the thing in the first place. It's coming up with some ideas that we can translate into this kind of crystallized form of ideas, an executable thing, this stream of bytes. And then once we have that stream of bytes, what we can do is, at the push of a button, we can clone it as many times as we like. What this means is that the economics of software are entirely different. Ours is not a production problem. We don't. There's no ongoing cost of reproducing new versions of the system. Really, it's essentially zero cost. So all of the cost is upfront in the design of this thing. So what this means is that we'd have to be kind of insane in order to do the same job again. Once we've got that stream of bytes that represents a system, we'll just reuse it for free, because what's the point of doing anything else? What that implies is that in the context in which we're doing our software, whatever it is that we're doing, we're always doing something new. We're always doing something for the first time. We're always exploring. We're not really trying to organize for repetition. And when we try to, that's just a bad idea, because that's not how software development works. That's looking at the solar system with the wrong model. As a result of talking about software engineering, which I've been doing for a few years now, I get in a surprising number of conversations about bridges. And it usually starts, yes, Dave, but software development isn't bridge building. And yeah, of course, that's true. But I also think it's true that we don't really think of bridge building in the way that's true either. If we're building something new for the first time, this is a picture, an early prototype of Elon Musk's and SpaceX's Starship, the supposedly reusable spaceship that's going to dramatically improve our access to space and the rest of the solar system. But if we're doing something entirely new like this, that's not the same as doing it for the 50th or the 100th time. So doing it for the 50th or 100th time is the production problem. Doing it from scratch, new, is the design problem, the engineering problem. And that's a very, very different kind of thing. This is a slightly more up-to-date picture of the Starship. This version blew up a couple of weeks ago in launch, in testing, trying to evaluate things. Now, when you're building new things, you're going to explore, you're going to try out the different parts of the system and evaluate those, and things will go wrong. And then you're going to try other simpler abstractions of what it is that you're doing, and things will go wrong. And you're going to try all sorts of things. This thing that looks like a water tower is one of the prototype rockets, and this was one of the first things that flew, a prototype of the Starship machine. And here it is flying, and eventually you get to something that you can use, something that's more repeatable. This is how real engineering works. Engineering is not ever a cookie cutter process. Engineering is about exploration and discovery. And that means that changes the way that we should think about it and the way that we should practice it. I'd argue that software development too is all about exploration and discovery. What that means is that if we want to become good at it, we need to become good at learning. We need to be good at exploration and discovery. And to do that, I think that there are 5 things that are essential in that approach. First, we need to work iteratively. We need to do things in small steps, try them out, and see which ones work and see which ones don't. A bit like SpaceX trying things out and sometimes blowing up rockets. We need to gather feedback. We need to, after each tiny step, we need to inspect the results of that step and determine whether that's moving us closer or further from our desired destination. This is describing really a process of incremental development, where what we're doing is that we're not thinking very hard and coming up with some amazingly clever idea about how this should all work. What we're doing is that we are essentially evolving our system, small step by small step. We're growing it more than building it from scratch. And the fundamental assumption here, I would argue the more scientific approach, the more scientific assumption, is to assume that some of our steps will be wrong, and therefore we want to work in these small, simpler steps, gather feedback, produce, grow our system step by step, and learn at each point so that we can quickly identify the steps that are wrong. That means that we need to be working experimentally. We need to be trying stuff out, seeing what works, seeing what doesn't, preferring the things that do work and fit where our goals, and discarding the things that don't. And finally, I think one of the distinguishing characteristics of engineering rather than pure science or mathematics is that we need to be empirical. We need to be absolutely also learning from the real world. Engineering progresses sometimes over centuries in a series of steps and gets better and better and better over time. One of my favorite descriptions of engineering in general is engineering is just the stuff that works. So if whatever it is that we're doing isn't working, we should discard that and find something better, because engineering is the stuff that works. It's hugely pragmatic, hugely practical. Software development, as well as being about learning, is also about managing complexity. We need to be able to do things that allow us to create these complex systems, hold them in our heads, work on them in one part without disturbing or breaking another part of the system. And that ability to manage the complexity of the systems that we build in, I would argue, is the other pillar on which software engineering and software development is or should be built. To optimize to manage complexity, I've got another 5 things. And these things will seem familiar to you, I am sure, because they've been around a long time. And I think that's important, because the reason that they've been around a long time is because they are deeply true. Now, I'm going to describe 5 things, and notice that I'm not really talking about any particular technology here. Good software is modular. It uses abstraction to establish seams in the design of our system so that we can interact with another part of the system without knowing or caring too much about how it works. It uses a separation of concerns where each part of the system is focused on achieving one part of the job. We don't want to bundle together the concerns of, I don't know, doing a tax calculation with storing that in a database or gathering the information from a user interface. We'd like to separate out those concerns and any other concerns that are involved. So at each layer, at each level of granularity, we want each part of the code, when we look at it, to clearly be working on a single thing. We prefer loose coupling. Now, just saying loose coupling isn't quite enough. We want appropriate levels of coupling, but with a preference towards looser coupling. The reason why that matters is, once again, so that we can work in one area of the code and change it without forcing change on other areas of the code. And finally, we like our code to be cohesive. We like all of the related things to be close together. You could think of modularity and cohesion as kind of opposite ends of the spectrum. One of my favorite descriptions of great design in software is to move the things that are unrelated further apart, that's modularity, and move the things that are related closer together, that's cohesion. I want to give you a bit of a practical demonstration of what it is that I'm talking about, because I think all of these things, they sound generic and general, and everybody in the audience is probably nodding their heads wisely and saying, yeah, I understand what you mean. But I'm saying something a little bit more specific. I'm saying that every time you make a decision in your life as a software professional, prefer the route to being more iterative, gathering feedback, working more experimentally, and so on, and make choices based on improving the modularity, cohesion, separation of concerns, abstraction, and reducing coupling in your code. And if you just do that, whatever the nature of your code, whatever the nature of the problem, I guarantee you a better chance of success. That's not the same as guaranteeing you success. There's no guarantee of success. But by just preferring these 10 ideas to the alternative, what you're doing is that you're ruling out a whole bunch of the dumb ideas. And so now what you're picking from is the range of better ideas. And so that improves your chances of success. So let's have a look at this in practice a little bit and just see how it lands. So let's start by thinking about, what does good code mean? Well, first of all, obviously, to be any good, it has to work. And after that, it needs to be modular, because we want to be able to change it separately and loosely coupled and cohesive with a good separation of concerns and exhibiting information hiding or using abstraction. All of these things, I would argue, are hallmarks of good quality code. I think it's hard to imagine anybody that would prefer not modular, tightly coupled, loosely cohesive code with a very poor separation of concerns and no abstraction. That would be, we have a name for that kind of system, and it's not a good name. They're big balls of mud. These are the kinds of systems that we hate working in. So we want these systems that are more like this. So in order to be able to apply this kind of engineering thinking, we need to optimize for learning, optimize to manage complexity using these kinds of these techniques, prefer the techniques that are the hallmarks, that lead us in the direction of the hallmarks of high quality code. To do that, to work more experimentally and so on, we need to control the variables. We need to think about how we're going to manage this in a repeatable, reliable way. So things like infrastructure as code, deployment pipelines, automated testing give us great feedback on our changes in a repeatable way. Continuous integration and so on. We want to make evidence-based decisions. We want to run the experiments rather than just guessing and thinking that we're brilliant and crossing our fingers. One of the tools that we can use to drive some of this decision is testability, striving for more testable code. So let's just think about that for a minute. My preferred way of working is test-driven development. But before that, what drove quality? If we think of those 5 properties as markers of quality in our code, what made us put those things into the code? Well, I think it's just this: the skill, experience, and integrity of a programmer. If you have the skills to do it, if you have the experience to recognize that it's important, and if you're having the kind of day where you care enough to be able to do this, then that's what it takes to build high quality software, or that's what it took. But TDD is something very specific. TDD is best captured by this idea of red, green refactor, and doing that repeatedly. The idea is that we're going to drive the development of our software, whatever our software is or whatever it's doing, from tests. We're going to start with a specification of what the software is meant to do, and then validate that it's doing that thing as part of the development of the system. The way that we do that is that we're going to write one of these tests, one of these little specifications, and run it and see it fail. That's red. And then we're going to do just enough change to the code to make the test pass, so that we can get back to a stable position. That's green. And then we're going to refactor the code and the test to make them more readable, more elegant, more generic, more beautiful, whatever it is that we care about, while we're in the stable position of knowing that the software is working because it keeps passing because it's green. That's the idea. And if we think about that, we'd have to be some kind of strange, crazy person to make our own life more difficult in doing this process. We're going to start by writing a test before we've got any code. So it's inevitable that by doing that, we're going to try and make our own lives more easy by writing a test that makes it easy to write the code, and writing a test that's going to be durable in the face of us wanting to change the code at some point as well, perhaps. So what is it that makes code testable in this way? Well, first, it has to work, of course. And one of the things that's important in testable code is that it's modular. We want to be able to test the pieces independently of one another. We'd like those pieces to be loosely coupled so that we can test them, and we haven't got to do a lot of complicated setup as part of the test to verify that the piece that we're testing is doing what we think it is. And we'd like the code to be highly cohesive so that when we're testing one part of the code, we're not worrying about what's going on in another part of the code. And we'd like a good separation of concerns. We'd like each of these parts to be focused on solving one part of the problem, so we can isolate that part of the problem and explore it and test it with some diligence, with some care, but also in the abstract, away from other concerns that we're not interested in when we're looking at this piece of code. If we're testing our VAT calculation, we don't really want to also have a database and a user interface to worry about at the same time. And we'd like to exhibit information hiding or have lines of abstraction so that we can interact and verify that our code can interact with other parts of the system without it actually having to interact with them. We can kind of fake those out. That's a nice example. So before test-driven development, the thing that drove quality in our code was the skill and experience of a programmer. And with test-driven development, this also drives quality into our code. Striving for testability amplifies the properties of that we identified as markers of quality in our code. So what this means is that we get this amplifying effect. I don't recommend that any programmers should take their brains out when they're practicing test-driven development. I think you still bring your skill and experience and integrity on the day, but you amplify it with test-driven development. It's my observation, having done test-driven development in a variety of different teams and circumstances for many years now, that TDD is the closest thing that we have to a talent amplifier in software development. It doesn't matter whether you're good or bad at software development. If you practice TDD, you'll be better. I've introduced a few programmers that I consider to be amongst the best programmers in the world to test-driven development, and they and I think they're better now. I've also helped to some less great programmers on the journey to TDD, and they're better too. So it's not going to make a bad programmer great, but it will make a bad programmer better and a great programmer greater. And we don't have many things that do that, really. So let me give you a little bit of an example of pulling this together and describing what it is that we're talking about. So here's an example of some code. Here's a car, and in this car we've got a petrol engine, and then we've got a start method that's going to put the gears into neutral, apply the brakes, and start the engine. And so let's write a test for this car. So here's my test, should start car engine. We're going to create a new car, and then we're going to start the car, and now there's nothing that we can assert. This code isn't testable at all. So we could do vile things, and we could break encapsulation of the code and so on, but that's just a really bad idea, and that's not going to succeed. We're going to end up with the tests that are too tightly coupled to the system and broken encapsulation, and now we can't change the code without breaking the test, and that's just going to be a nightmare. So this is just not good enough. This is not testable code. So let's start again only from the point of view of testability. So we're going to solve the same problem, but we're going to do this thinking about the testability of the code. So let's start with a test. So let's say what we want to be able to do at the end is check that the engine was started successfully. So we'd like to be able to assert that that was the case. So that's going to happen when we started the car. That makes sense. And in order to do this, we're going to need a better car. So we're going to need a car where we can pass in the engine so that we can tinker with the engine first. So now we're going to create a fake engine that allows us to check that it's been started successfully, and the rest of the test is essentially the same. Yes, I'm just talking about dependency injection. But let's look at the impact of that. So here's my fake engine. So all this does is that when start on the engine is called, it just records the fact that the engine was started so that we can query it later on. It's very, very simple. I'd probably use a mocking library to do this in reality, but it's just, I just wanted to be able to demonstrate more clearly what was going on here. So here's my better car. Here's the test. The better car is using the dependency injection. So let's just think for a moment about the implications of that on the design of our car. So here's the better car compared to the car. And as I said, the only difference here is the use of dependency injection. But that simple step that was forced on us really by a desire for testability in the code it was kind of a little bit less than a conscious choice, because we needed to do that to make this better car work and to make our code testable. So the impact of that on the design of our code is that our code is now more modular. Previously, the car needed to understand how to create petrol engines. This version of the car doesn't need to know that. So it's doing less, which means it's also more abstract. It's more divorced from the petrol engine-ness of a petrol engine, and it's talking in more abstract terms. That means that we've also reduced the coupling in this design. It's more cohesive because all of the stuff here is now specifically more closely related to what we're interested in, the car and its interaction with the engine. The actual details of how you create that engine and so on were superfluous before, and so we're really breaking the cohesiveness of this code. So it's more modular. It's got a better separation of concerns. It's better cohesion. It's got nicer lines of abstraction because we're talking about engines, and it's reduced the coupling. This has amplified all of those properties that I mentioned earlier that I think represent good markers for quality in our code. What the result of this is that this better car is better not just because I say so. It's better because it's more flexible. It's better code. If I want to create exactly the same kind of car as before, with a petrol engine, I can still do that. And if I wanted to create a car with an electric engine without changing any of the code in the better car, I can do that. And if I'm some kind of crazy person, I can even create a car with a jet engine if I want to. All of this without changing the code that I've already written. So that code is more flexible, more useful. It's simpler. It's easier to test. And it's just better based on those 5 properties of what we consider better. One of the other tools that we can use for making progress that I mentioned before is working experimentally, to help guide us on our engineering exploration of a problem. We can try things out in small pieces. You could think of the software equivalent of this as being a unit test. This is a spaceship unit test going on right here. We need to be able to be comfortable with things going wrong, because that's a good thing. If we learn as a result of our experimentation and our tests that we made a mistake, that's much better than waiting out to find out sometime in production later, or by losing lots of money or killing lots of people, that our choices were wrong. Our objective as engineers is not to expect perfection, but instead to work in ways that if we are not perfect, which is usually going to be the case, then we can recover from it safely and ideally cheaply. And then we can try out our ideas on small scales and bigger scales, and we can start to grow our systems more incrementally. This idea of working in small steps is really, really foundational, both to engineering discipline in general, but also, I would argue, to the way that the scientific method, the humanity's best problem-solving approach. For this, we need to be able to gather feedback to learn from what's going on. We need to predict the results of what's coming next. And again, automated tests are one extremely valuable form of experiment. We need to take control of the variables to make sure that we get this repeatability and reliability into our process. I often use this little diagram to describe my preferred approach to applying these kind of engineering principles, continuous delivery. We're going to optimize from idea to valuable software in the hands of users. We're going to use techniques like test-driven development at the center of this feedback loop for a very, very fast feedback on, does the code do what I think it does? And we're going to use ideas like executable specifications, other forms of acceptance test, of automated tests, to validate that the software does what our users want and is releasable. And all of these things are allowing us to make progress in smaller steps and to give us constant feedback on the correctness and utility of our software. This is a quote from nearly everybody's favorite physicist, if you're the kind of person to have a favorite physicist. Sorry, I pressed the button too soon. Step back. It doesn't matter how intelligent you are, if you guess, and that guess can't be backed by experimental evidence, then it's still just a guess. So our job, if we're trying to apply a bit more scientific rationalism, which is what I describe engineering as, to solving problems in software, is to figure out a way to move away from just guessing. Guessing has a part, but in science and in engineering, we guess and then we test our guesses. We don't just cross our fingers and hope that the guesses are correct. The other tool that we can use, surprisingly, is speed. By moving more quickly, that kind of forces us to work in smaller steps. This is a traditional cycle time. And this is from a real project in a bank some years ago. And this bank couldn't make a single line change to their production system and follow their own development process in less than 103 days. This is the cycle time from a project that I worked on where we built one of the world's highest performance financial exchanges using the kind of engineering principles that I'm talking about today. And this is a typical continuous delivery style cycle time. In this project, which was about 15 to 20 times bigger than the project on the top line, we could make any change to our entire enterprise system and evaluate it in under an hour and get a definitive answer back is it releasable? That kind of feedback simply changes the game. And optimizing for that is one of the things that can drive us in the direction of greater success. Continuous delivery is about working. It's the first principle of the Agile Manifesto, which is our highest priority, is to satisfy the customer through early and continuous delivery of valuable software. And it gives us a lot of profound insight into the quality of our work and the efficiency with which we're doing it. We create a repeatable, reliable process for releasing software, and we do that through automating and version controlling pretty much everything. This is a quote from a few years ago. If agile software development was the opening act to a great performance, continuous delivery is the headliner. I would argue that continuous delivery is a genuine engineering approach to software development. And it's these days it's proven. We don't have to be shy about the fact that this is state of the art for software development. This works better than anything else that we know of. Continuous delivery is deeply grounded in these sorts of engineering principles. We build things like deployment pipelines, and the idea of these is to give us that iterative way of working, that experimental way of working. We can make a change, we can try it out, we can evaluate it in safe, controlled circumstances. This is the experimental part. We then have our deployment pipeline, and we can get feedback in under an hour over whether our experiment is good or bad. So we optimize to be able to deliver, to get feedback on from commit to releasable outcome multiple times per day. And again, this is part of our engineering discipline. We're preferring fast feedback, we're preferring high quality feedback, and we're preferring evidence-based decisions based on the evidence that we gather from evaluating our changes rigorously and repeatedly. This is really optimizing for in multiple stages. So we're optimizing for continuous integration to deliver feedback. Usually I recommend in under 5 minutes to development teams to be able to tell whether their change is doing what they think it's doing. And then we look at the releasability of our changes. Does it do what users want it to do? Is it fast enough? Is it resilient enough? Is it secure enough? And we evaluate those. And generally, I recommend that people aim to try and do that in under an hour. This is what we mean by fast feedback, genuinely fast, within the same working day. And the reasons why these things matter is fundamentally what we want. The marker, I would argue, of quality in software is that it allows us to change our minds, to make mistakes, to recover from mistakes. So we want to be able to retain the ability to change our software. I would argue that that is the number one defining characteristic of high quality software versus any other kind of software. And if we're looking to apply a more engineering focused approach and amplify our creativity as software engineers, whatever it is that we're doing, if it doesn't allow us to build better software faster, it doesn't account as engineering, and therefore we should change it. Thank you very much. I'm sorry that I ended up starting late because of the technical difficulties, but I hope you've enjoyed my talk. And I know I've whizzed through that quite quickly, but check out my YouTube channel if you'd like to see some of these ideas explored in a bit more detail. Thank you very much.
All right, thank you, Dave. We are a little bit late, but maybe we have time for one question. If you have to run, please go for it, because I know we're in the break, but there's one question here that maybe might be interesting for the audience. Do you think that AI today is empowering worse software development? It is possible to generate tests, meaning don't experience pain working in bad design.
I think at the moment AI is not quite there for software development yet. I did some playing with AI, and one of the things that I found is that I needed test-driven development, because AI at the moment, the current versions of AI, I think that the new Google one that they've just announced, the new version of Palm is better. It validates some of its code, but certainly GPT-4 and earlier versions did not. And so they would just generate garbage. They generate stuff that didn't work and stuff that solved different problems to the problems that you're asking for, as well as giving good solutions. They are remarkably amazing pieces of technology. So what the conclusion I came to is if I was using AI for writing software, I wanted to write a test first so that I could validate that the software that I was writing did what I wanted. And I think that that's probably the direction that software engineering, software development will take. Our job will become essentially raising the abstraction at which we're programming. We'll be programming through prompts and validating what has been written by the AI, because we can't trust the AI to have written the things that we've asked it to write yet.
Gotcha. Thank you so much, Dave.